Okay, so we're going to have a look at transitional metal complexes, and we're going to take copper as an example, and copper 2, which is 2 plus, and we're going to surround this with 6 H2O ligands, which gives an overall charge of 2 plus as their neutral. Now if we add something like 4 ammonias, NH3, the product we're going to end up with is copper, still 2 plus, no change there, and 2 H2Os, water, and 4 NH3s. And as NH3 is neutral as well, this is still 2 plus. Now we're going to look at this example as it's a little bit more complicated, but it actually has virtually the same geometry as this, which is octahedral. Okay, so if we draw out a square to start with, which is the base, and if we then draw some points from there, like so, what we end up with is your octahedral, which has 6 points, 1, 2, 3, 4, 5, and at bottom 6. And if we imagine our copper in the centre, like that, it's going to be surrounded by 4 waters, like so. This is why I drew a square at the beginning, if you remember, because that's how they arrange themselves in like a square. And then at the top and the bottom, we're going to have the ammonias. Now just to draw these out, that is going to look like that, which again is like a little tetrahedral, whereas these are going to be drawn like that in the plane. Now obviously the thing that these two ligands have in common is that they're donating with lone pairs, like so, which are negative going towards the positive metal centre. As you can see from this, we've got our octahedral all drawn up, but as chemists, the way you'd actually draw this, which is a lot easier and a lot less lines, is you'd draw it like this, with these two in the same plane, the waters coming towards you like this, as part of this square that we drew at the very beginning, and then going away from you like so. However, whether you've seen the clip before, we've mentioned that the wedge, this dark one, is coming towards you and these are going away from you, and that's the sort of classical notation that we use quite a lot. As you can see, it's also in the ammonia drawing as well. Now if we just get rid of this for a minute and look at a slightly different reaction, this time it's going to be a little bit more complicated, because we're going to start off with the water atoms surrounding it, and 2 plus again, and that's actually called a hexaquion if you wanted to use its correct term. This time we're going to use 4 of these Cl minuses, which I should probably put there, and the difference is this time not only have we got rid of all of the water, they've all gone, so we've got put them down here just to balance the equation. This is still 2 plus, however if we look at the sums, these are all neutral, so it's 0 times 6, and that's your 2, gives us your 2 plus. This is still 2 plus, but we have 4 times minus 1, so overall that's 2 minus. Now we need to have a look at the shape of this. As you remember, that's the octahedral, quite happy with that, the one we've seen before, but this one however is actually tetrahedral, which no doubt won't be too difficult for you to imagine, because you've all done the carbon model kit type structures probably in class, which if we draw this out using the wedge, the copper complex, and we've got a chlorine there, there, and there. If we drew some sort of little lines between them, we can see that you're actually forming a tetrahedron, which is quite nice. Four-sided pyramid.